Maps have been around pretty much since we first started exploring, but they were basic. You fast forward to 2016, you put some lasers in the sky and some sensors in the water, and our impressive coastline has never looked so good.
This is Pictou, Nova Scotia.
Some good swells now.
Today, a team of researchers is collecting data from above and below to create a seamless map of the shoreline.
Our particular sensor can measure both the land and under the water.
Traditional maps are good at surface information to get us from point A to point B. But these guys are using special LiDAR that shoots laser pulses through the water to measure the seabed.
And not only do we have the laser on board, the two lasers, we also have a high-resolution camera that takes pictures in the visible and the near-infrared spectrums.
Put them together and it's called elevation mapping. And Tim Webster's team is at the forefront in coastline surveys.
We're the only academic institution in Canada to own one, the Nova Scotia Community College. And to my knowledge, we're one of the few research groups that are pushing the boundaries of how the data is used for different things other than simply mapping where the deepest channel is for nautical purposes.
For the first time, maps will show both the land surface and the sea floor along the coast.
Canada has the largest coastline in the world. We don't have very good maps of our near-shore areas. So that's why it's important for both coastal development, preserving coastal ecosystems, and looking at how things are changing with climate change.
Or simulating an oil spill in 3D. Tim's team created this precise 3D model of the Strait of Canso, a busy petroleum shipping route, to show what could happen if there was an oil spill.
Many of our coastal areas, tankers bring fuel and petroleum products to and from port, and if there were an oil spill, we don't have good information on the near-shore currents. And that, of course, is critical to the responders, the cleanup responders, to know how long they have prior to doing that.
Today, they have a different goal.
This is the Abercrombie pulp mill across from us.
Every day for decades, this mill has dumped millions of gallons of toxic wastewater into the harbor.
And the effluent from that plant is currently being discharged into the outer harbor after it goes through treatment.
Well, that treatment plant is scheduled for a shutdown within a few years. Creating a digital model now is crucial so they can track changes as the area is cleaned up and return to its former glory.
So we're here to collect baseline information on what the ecology is as well as the geomorphology.
For lasers to work, they need clear water, and that's what we're hunting for.
Because LiDAR is using light, we're very much limited by the water clarity. So if it's a day when the water is murky and dirty, then the laser will not go very far. The light will get scattered by the particles in the water. Okay, so I think we'll start our first point here.
That's where a Secchi disc comes in handy.
We use this to judge how clear the water is. So I lost sight of it where my hand is, about there. The laser should be able to do 1.5 times whatever that depth is.
My name is Candice McDonald. I'm a remote sensing specialist, and today I am taking GPS points and recording the data we observed.
Secchi depth was 2.2.
And did it disappear? Okay, so it disappeared.
I'm Jesse Siegel. I'm a research assistant. Today I'm manning the quadrat drops.
A quadrat gives them a reference point for size and location of the samples.
We have our GoPro camera set here to take a vertical shot of this 50 centimeter by 50 centimeter grid, and we're going to lower it over the side and see what's on the seabed. So then we'll let it sit there for probably a minute or two. It's taking pictures every 5 seconds. So this is an AML water quality probe, so we use this to get a profile of the ocean. This instrument is probably the most precise way to measure the temperature, the conductivity, and the turbidity of the water itself.
This tool, the ADCP, Acoustic Doppler Current Profiler, measures the flow.
We can tell both the direction and the speed of the current, or the particles, from that. So we use this whenever we're at an estuary or a river in order to understand what the flow of the river is.
The data collected in the water combined with laser-sharp detail from above create a powerful mapping tool.
So the information we collected today on the boat, we'll use that when we interpret the LiDAR, and we'll use those data to better interpret our maps and produce maps of, say, what's on the bottom in terms of the aquatic vegetation.
The result is an animated, exact rendering of the area, which they can use to carefully track changes to a fragile ecosystem.
It is our goal to do repeat surveys because after winter storms, channels change, sandbars move, and so on. So it's important to be able to do repeat studies where the technology will show you the same information, the same answer,